Solubility rules in water. You know them or you don't. Start off with a question about general solubility. Why does anything dissolve? Well, when you have the IPFs in the solution are not costing you significant energy compared to the IPF in the pure substance. So the IPFs in the solution will either be equal to or greater than the IPF in the pure substances, notably the solute. So as we go through here, let's look all the way through our pure substances. There's water. Well, we certainly don't have induced dipole forces between water molecules. We don't have induced dipole between copper and sulfate. If we did have strong attraction between copper and sulfate, it wouldn't dissolve in the first place. Hydrogen bonding in the water molecules, absolutely, but if that was a reason for solubility, well then nothing or everything would have the same solubility because water always has hydrogen bonding. But what is important in the solution is making the new ion dipole forces between the ions and the water molecules. Following soluble in water, well, let's see, we have an iodide. One of the rules says that an iodides are soluble unless the cations are silver, lead, copper plus, or a variety of mercury containing ions. So lead iodide is insoluble in water. AgSO4, we know some rules about sulfates. Sulfates are soluble unless the cation is, looks like the same list, except you lose the copper plus and you add in the heavier alkali earth metals. So calcium, strontium, barium sulfates insoluble, but we care about silver here. Lithium phosphates, well, phosphates are insoluble unless the cations are alkali metals or ammonium. Conversely, all alkali metal salts are soluble. So that one's going to be soluble. Finally, aluminium hydroxide. What do we know about hydroxides? They're insoluble unless the cation's an alkali metal, ammonium, strontium, or barium. So aluminium hydroxide, insoluble. Which cation forms an insoluble chloride, insoluble sulfide? Well, let's see. We know that lead has an insoluble chloride. Most chlorides are soluble except for silver, lead, mercury, and copper plus. Okay, sulfides are all insoluble unless the cation is an alkali metal, ammonium, or an alkaline earth metal. Lead is neither of those, so as an insoluble sulfide. Manganese 2 plus, well, it's not one of the list of insoluble chlorides, so it's a soluble chloride, but everything with a sulfide is insoluble unless it's an alkali metal, alkaline earth metal, or ammonium, and manganese is a transition metal, so it's an insoluble sulfide. Iron 2 plus, going to be the same as manganese 2 plus. Barium 2 plus has a soluble chloride because it's not one of the list, but it's an alkaline earth metal, thus it has a soluble sulfide. And finally, calcium 2 plus, going to be the same, soluble chloride, soluble sulfide, because it too is an alkaline earth metal. Thus the only one that has both insoluble ones is lead, and there's a little bit of flashing for lead. Which soluble ions falls the smallest number of insoluble salts? Well, sulfates, we know that it's soluble except for 5 ions that I list out for you. I actually think there might have been 6, so it's silver, lead, mercury, and then the 3 heavier alkaline earth metals. Hydroxide, all insoluble except alkali metals, ammonium, barium, and strontium. Carbonate, all insoluble except alkali metals and ammonium. Nitrate are all soluble, and chloride are mostly soluble except, of course, for silver, lead, 2 mercuries, and copper plus. So therefore nitrate has the smallest number because it doesn't have any. Dissociation calculations. Well, the important thing here is that ionic substances dissociate when you put them in water. So when we look at the sodium sulfate, concentration 4.4 moles, we don't know, 0.25 litres, multiply that out, so that's 1.1 moles of sodium sulfate. But sodium sulfate is ionic, it dissociates to give us 2 sodiums and 1 sulfate. And so therefore we've actually got 3 ions for the price of 1. So the number of moles of ions, 3.3 moles. 1 mole of each of these dissolved in enough water to make 1 litre of solution. Important side note, that's how you make solutions. You don't take 1 mole and add 1 litre of water. You take 1 mole of the solute and add enough water to make 1 litre of solution, and it's not going to be 1 litre of water. Anyway, so we effectively made a 1 molar solution of each of these, which would have the highest concentration of ions. Well, ionic substances dissociated to ions. Lithium chloride is ionic. This glucose covalent, then we have ionic and ionic, so we can ignore the C6H12O6 because that's covalent, so it's not going to have any ions anyway. Lithium chloride splits into 2 ions, lithium and chloride, so thus it will have 2 molar of ions because it was 1 molar lithium chloride times 2 is 2 molar. C6H12O6 is 1 molar, but it's of molecules. MgC2H, the magnesium acetate, this is, funny way to write acetate, so that gives us 3 ions, so it's 3 molar concentration of ions, but aluminium nitrate splits up into aluminium and 3 nitrates, so that gives us 4 moles of ions. Essentially same question, soluble ionic substances dissociate, covalent don't. So sucrose doesn't dissolve into ions, just like glucose didn't in the last question. Now calcium chloride, we got moles, well it's 0.3 litres times 0.1 molarity, so 0.03 moles of calcium chloride. Calcium chloride splits into 3 ions, so therefore we'll have 0.09 moles of ions, 0.03 times 3. FeCl3, number of moles is 0.02, 0.2 times 0.1 is 0.02, splits up into 4. So therefore that's going to be 0.08, 0.02 times 4. Sodium chloride, 0.04 moles, splits into 2, so that's 0.08 as well. And in the KBr, 0.02 moles KBr splits into 2, so that will be 0.04 moles of ions. So the one that gives us the most ions, the calcium chloride, because there's more moles of calcium chloride that split into their ions. So we're now doing a combination. I always like these. I like to draw little pictures for it too. 50 mils, 0.2 molar NaOH. So that's going to be 0.01 moles of NaOH. And of course NaOH dissociates into sodium ions, don't care, plus hydroxide ions, 1 hydroxide ion from 1 sodium hydroxide, so 0.01 moles of hydroxide. So that's a little picture, 0.05 litres that contains 0.01 moles. The one I'm doing in blue, 75 mils, 0.1 molar NaOH, so that gives us a total of 0.0075 moles of NaOH, 0.1 multiplied by 0.075 litres. Draw a pretty little picture of that. So this is 0.075 moles of OH minus in 0.075 litres. Put them together. Well, we got 0.01 plus 0.0075, which gives us 0.0175 moles. Put the volumes together, 0.05, 0.075, we get 0.125 litres. You can assume here volumes are additive because very dilute solutions and the same solvent. So concentration of hydroxide is the 0.0175 divided by 0.125, which is 0.14 molar. Finally, precipitation reactions that of course require knowledge of your solubility rules. Spectator ions in a reaction between copper 1 nitrate, potassium bromide. Well, first of all, write out what the double displacement reaction will be. You're just swapping around the ions, so copper 1 will go with bromide and potassium will go with nitrate. We know copper nitrate is soluble because all nitrates are soluble. We know KBr is soluble because all potassium salts are soluble. CuBr, well, Br are all soluble unless the cation is Ag plus, lead 2 plus, the mercury is all copper plus. Thus that is insoluble. And potassium nitrate, of course, all potassiums are soluble, all nitrates are soluble, so that will definitely be soluble because 2 solubles do not make an insoluble. So the copper bromide is insoluble. Let's put in little aqueouses and the solid for the insoluble. Break it up into the ions. So we have copper plus nitrate there because solubles dissociate. K plus Br minus because solubles dissociate. Insolubles don't, so we leave it there. And K plus NO3 minus because solubles dissociate. Compare both sides. And we see that nitrate is the same on both sides. Potassium is the same on both sides. So the spectator ions K plus and Na3 minus. And the net ionic equation is Cu plus aqueous plus Br minus aqueous goes to CuBr solid. Which following reactions not be a visible change when reactions are mixed? Well, spread out a bit. So our products here of lithium chloride and silver nitrate will be silver chloride and lithium nitrate. Okay, silver chloride is insoluble, so we will make a precipitate, so there will be a visible change there. Barium perchlorate and lead nitrate makes lead perchlorate and barium nitrate. Well, all perchlorates are soluble, all nitrates are soluble, so there will not be any precipitate of any kind here. So therefore there will not be a visible change. So we'll check on that in a minute. Keep going. Right, Na2CO3 plus HCl, where you intermediately make this carbonic acid, but carbonic acid breaks apart to give you water and carbon dioxide gas. So you'll see a visible change because it bubbles. Ammonium chloride, KOH, where you make ammonium hydroxide. Ammonium hydroxide, however, breaks apart to give you ammonium gas, so that bubbles away. These are two nice tests respectively for acids and bases. And then copper perchlorate plus copper 2 chloride. Well, you make copper chloride, which is insoluble, so it's a nice little precipitate. So precipitate, nothing, gas, gas, precipitate. The only one with no visible change is that second one, which I have nicely arrowed there. Which following reactions aqueous solution net ionic equation be the same as that for copper perchlorate plus potassium hydroxide? Well, let's investigate the reaction first of all. We're going to make copper 2 hydroxide and potassium perchlorate. There's the formulas. All perchlorates are soluble, all potassiums are soluble, all potassiums and perchlorates are soluble, all hydroxides are insoluble unless the cation is ammonium, alkali metal or strontium or barium. Copper 2 is not one of those, so this is going to be a precipitate. So thus the net ionic equation for this is the copper 2 plus that was in aqueous solution, the two hydroxides that were in aqueous solution, making the copper 2 hydroxide solid. So looking at all the possibilities, the only one that's got copper 2 in one and hydroxide in the other is this second one. Let's just work it out. Copper 2 acetate plus sodium hydroxide goes to copper 2 hydroxide plus sodium acetate. Okay, the sodiums are going to be spectator ions because they're aqueous solution there, aqueous solution there. The acetates, all acetates are soluble, so spectator ions here, spectator ions here. Copper 2 plus in solution, 2OH minus in solution goes to copper hydroxide in the solid. So the last question about making precipitates, which of course serves as part of the tests for a lot of ions in solution. We need to know about silver plus and barium 2 plus. Now both of these are ions that have exceptions to the rule. For example, halides, chloride, bromide and iodide, usually soluble, but there are 5 insoluble, including silver. There are sulfates, mostly soluble, some insoluble, including silver and barium. On the flip side, most hydroxides are insoluble, except, of course, barium is one of those that is soluble. Most sulfides are insoluble, except barium is one of those that is soluble. So let's go through these ones here. Now, when we've got, if carbonate is present, all carbonates are insoluble, except ammonium and alkali metals. So thus silver carbonate should be insoluble, a precipitate. Barium carbonate, however, is insoluble, so should be a precipitate. So there we are. We would expect a precipitate silver carbonate, but we would actually expect a precipitate of barium carbonate, so therefore this is not one that would be seen. Okay. Hydroxides, what do we know about hydroxides? All insoluble except those, blah, 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 blah. So silver hydroxide should give a precipitate, so this is wrong. And barium hydroxide should not be a precipitate, so that too is wrong. Okay, iodides, well, they're like the chlorides, all soluble except silver, lead, copper, blah, 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 blah. So silver iodide would be insoluble, so we'd expect a precipitate. Barium iodide, soluble, so we would not expect a precipitate. So both of those, right, but are listed would produce the results given for it. Okay, so iodide looks good. Let's check with the sulfides. All insoluble except alkaline metals and the alkaline earth metals and ammonium. So silver sulfide should be insoluble, should give a precipitate. Barium sulfide, one of the exceptions here, should not give a precipitate, so that's correct. So there you go. It's a rather confusingly worded question, but one that tests the concepts nicely. Iodide would indeed give a precipitate with silver and no precipitate with barium.